Hi, I'm Massimo Bartoletti, and I will present joint work with Letterio Galletta and Maurizio Murgia. Ethereum is the centralized infrastructure to exchange crypto assets according to programmable rules. The programs that implement these rules are called smart contracts. Abstractly, Ethereum can be seen as a peer-to-peer network which stores a long append-only sequence of transactions, called blockchain. Some transactions, like T0 here, allow users to create new contracts. Here the contract C implements a simplified token. Tokens are one of the most successful applications of Ethereum and other blockchain platforms, as they allow to define various kinds of crypto assets. A famous example is CryptoKitties. This is a token contract to exchange collectible cats, which has received more than 5 million of transactions, processing sales for dozens of millions of dollars. Our token contract has a shared mutable state represented by two mappings, owner and balance. The contract has a procedure to transfer a token from a user to another one. Here we allow the transfer to happen if the sender of the transaction is the owner of the token, and if it coincides with the from parameter. Other transactions, like T4 here, allow users to invoke contracts. Here Alice uses T4 to transfer a CryptoKitty to Bob. Assuming that Alice is the current owner of Kitty 1, after the transfer the two mappings are updated so that Bob is the new owner. Transactions also contain a small fee which is used to incentivize their execution. The Ethereum peer-to-peer network is populated by two kinds of nodes, miners and validators. The miners, represented here as pet piggies, are those who can append transactions to the blockchain. A miner operates as follows. First, receive the transactions sent by users. Then, prepare a block of transactions and execute them in sequence to update the new states of all contracts and the balance of all users. 3. Solve a cryptographic puzzle, which depends on the prepared block. The first miner who solves the puzzle gets the right to append the block to the blockchain and to redeem all the included transaction fees. On average, a new block is mined every 15 seconds, containing approximately 2,000 transactions and paying $600 in fees to the miner. The other miners and the validators take the new block and append it to their local view of the blockchain. While doing so, they re-execute the sequence of transactions to update their view of the state of all contracts. Now, what is the problem with this picture? Both miners and validators execute transactions in sequence, without any concurrency, without exploiting today's multi-core and cluster architectures. This is a negative impact on the performance of Ethereum. For instance, a full validator node takes several days to synchronize. A low throughput is also a drawback for miners. If a miner is slow to execute transactions, it may be surpassed by another miner and lose the block reward. The good news is that this is a known problem, which can be addressed by using techniques from software transactional memory. The idea is to make miners execute transactions optimistically in parallel. Conflicts in the access to shared data are resolved by delaying or rolling back some transactions. In this approach, miners must include in the new block a serializable concurrent schedule of its transactions. This schedule is then replayed by validators, and it guarantees that all nodes agree on the current state. Dickerson and his co-authors have been the first to explore this approach. Their experimental setup is minimal, a 4-core processor with 12 GB of memory. In this setting, they have estimated a maximum 2 times speed up in the throughput of miners and validators. Even though this estimate has been computed on a small benchmark of smart contracts, I believe that there could be a significant speed up also in the wild. Unfortunately, there is a practical problem with this approach. The problem is that Ethereum nodes must revise the consensus protocol they use to have a coherent view of the blockchain. In particular, nodes must now accept the scheduling metadata included by miners in each block. Changes to the consensus protocol are only possible if the majority of miners agrees, and in practice they are very rare. In the worst case, we could end up in a hard fork of the blockchain. That means that Ethereum splits into competing cryptocurrencies. This has already happened in the past. For instance, a hard fork took place in 2016 to repay investors after the DAO attack. This hard fork caused Ethereum miners to split, giving rise to a new cryptocurrency called Ethereum Classic. So, the problem we have addressed in our paper is how to exploit concurrency in blockchains without changing the consensus protocol. This slide is just an overview of our approach. We have started by defining a semantics and an observational equivalence for blockchains, this tilde here. Basically, two blockchains B and B prime are equivalent if, after executing the transactions in sequence, all contracts in B are in the same state as those in B prime. Then we introduce two notions of transaction swappability. The first notion is purely semantical. Two transactions T and T prime can be swapped if the order in T prime is observationally equivalent to T prime T. The second notion instead is based on a static analysis of the variables read and written by transactions. We prove that this notion implies the semantical one. We then construct, starting from a block B, an occurrence net which represents the partial order induced by the swappability relation. This occurrence net can be used by miners and validators to concurrently execute the transactions in the block. The crucial point here is that, unlike the optimistic approach discussed before, ours does not require to include scheduling metadata into blocks, since anyone can compute the occurrence net. Therefore, our technique can be implemented without forking the blockchain. In the rest of the talk, I will give a few more insights on our constructions, and I will conclude by discussing the practical feasibility of the approach. The first notion of swappability is based on the semantics of blockchains. Two transactions, T and T prime, are swappable when exchanging their order preserves the observational equivalence. We show that the Mazurkiewicz equivalence constructed on this relation is an observational equivalence. Intuitively, this means that if we take a blockchain and we rearrange swappable transactions, then we obtain an observational equivalent blockchain. The problem with the semantical swappability relation is that it is undecidable, as the contract language is Turing powerful. So we introduce another relation which is based on a static analysis of smart contracts and on Bernstein's conditions for detecting parallelism. Assume that R and W are sound approximations to the set of variables read and written by a transaction. Then we define this sharp swappability relation here. T and T prime are swappable if the variables written by T prime do not overlap with those read or written by T, and vice versa. We prove that the sharp swappability relation safely approximates semantical swappability. For instance, consider these transactions from a user A to the contract C. The contract has three procedures, F, G, and H. A static analysis on F would say that F reads the variable X and can write Y. Similarly, G reads Y and writes X. The procedure H writes Z and reads nothing. Since the H does not touch the variables read or written by TF or TG, then it is swappable with both transactions. Instead, TF and TG are not swappable, since, for instance, F reads X, which is written by G. Now assume that we have a block B with TF, TH and TG. The swappability relation already suggests that we can execute TH in parallel with any of the other two transactions, and that we must preserve the order between TF and TG. To make this argument more operational, we exploit occurrence nets. Roughly, these are petri nets, where each transition can only be fired once. We define a construction that takes as input a block and the swappability relation, and gives as output an occurrence net which operationally describes the concurrent executions of the block. In our example, the output would be this occurrence net here. At the beginning, the net can fire concurrently the transitions TF and TH, while TG is not enabled. TG can be fired only after TF has been fired, so the net preserves their order as expected. The possible concurrent executions of the block P are represented by the maximal step firing sequences of the occurrence net. For instance, the first step firing sequence describes the schedule where TF and TH are executed in parallel, and TG after them. Note that there could be many different maximal step firing sequences in the same occurrence net. One of our results is a sort of confluence property, and it states that all these maximal step firing sequences represent the same state of the blockchain. We give a semantics to step firing sequences to model the parallel execution of transactions. This semantics executes transactions in isolation and then merges their changes. The merge is undefined in case of conflicts. In practice, this semantics can be implemented by instrumenting the runtime environment of contracts, so to record the state changes resulting from the execution of transactions. For instance, consider a state sigma, where x and y are 0. The semantics of the step TF, TH updates sigma by setting both y and z to 1. This corresponds to the semantics of the sequences TF, TH and TH, TF, coherently with the fact that TF and TH are concurrent. Note that the semantics of the step TF-TG sets both x and y to 1. This does not correspond to the semantics of any interleaving of TF and TG, coherently with the fact that TF and TG are not concurrent. This slide summarizes our main result. The theorem states that executing any maximal step firing sequence of the occurrence net is equivalent to executing sequentially the block. Summing up, our technique allows miners and validators to exploit parallelism without requiring a fork of the blockchain. This slide describes their workflow. Note that our paper does not address the problem of defining static analysis of contracts. We assume that some analysis exists, and building upon it, we give our constructions. I would like to conclude by discussing the practical applicability of our approach. Unfortunately, there is no clear answer, but only a few arguments in our favor. Let me start from a negative point. The bytecode language run by Ethereum nodes is not designed to make the analysis easy. So I expect that for many contracts, the result of the static analysis will be quite imprecise. This is very unfortunate, since verification would be crucial in a setting where immutable contracts handle hundreds of millions of dollars in crypto assets. Despite this, there is a point which makes me moderately optimistic. The fact is that a substantial amount of transactions in Ethereum operate on very simple contracts, like tokens. These contracts have a rigid structure which can be exploited to improve the precision of a static analysis. Note that even if static analysis were unfeasible, there are other approaches to improve the concurrency of contracts. For instance, some miners could accept, when a contract is created, a proof about its read-write behavior. This proof could be verified by the miner once, and its results used every time that contract is called. A related approach is to incentivize the use of domain-specific contract languages that, unlike Ethereum's native language, are amenable to verification. This would have the additional benefit of improving the security of Ethereum contracts, which, as witnessed by a long history of attacks, should be of primary concern for whoever invests money in them. Thank you very much.